Section 4.7, variation of parameters, is just basically more tools to help us solve differential equations. To start with this, first we recall the first order differential equation, either y prime or dy dx plus p of x y equals f of x, and I'm gonna call this equation 1. So such non-homogeneous equation has solutions with the general solution. Y sub g is the yc plus yp, complementary plus the particular, where the complementary solution, this is all from previous sections, c1 e negative the integral of p of x dx. Okay, this is basically the solution for the non-homogeneous equation, which is the left hand side of 1 equals 0. Let's call this equation 2. And y particular is e negative integral of p of x dx times the integral of e of the integral of p of x dx f of x dx. This part here, we're gonna assume it's u1. u1 is a variable parameter. That's where the name of the section came from. So this is a particular solution of equation 1. Note that yp is a multiple of yc, the complementary solution. So now this means yp here can be rewritten as this is yc, so yc times u1. So again, u1 is called variable parameter. Now what are we going to do with this? We're going to using reduction of order. So for y prime plus or dy dx, p of x y equals f of x with y1 is c1 e negative integral of p of x dx as known solution. We will find here the particular solution. The particular solution. So how do you do that? Well, we said y sub p is y1 times u1. So we're going to differentiate both sides using the product rule, y1 prime times u1 plus y1 times u1 prime. Then for the equation, we can substitute y prime p plus p of x yp is f of x, as this is the particular solution. We found y prime p is y1 prime times u1 plus y1 times u1 prime plus p of x times y1 u1 equals f of x. Then we group the u1 together, these two together. We have y1 prime plus p of x, or just p, y1 all u1 plus y1 prime y1 equals f of x. Now this one here, this is 0. Why is it 0? Because of equation 2 up there. So this is 0 by equation 2. So this becomes u1 prime y prime equals f of x. You can rewrite this as du1 over dx, or then separable. Separate that. F of x dx over y1, or y1 of x. Integrate both sides. You get u1 is the integral of f of x dx over y1 of x. Then y, which we define as u1 y1, is y1 or y1 of x, the integral of f of x dx over y1 of x. But we have something for y1. It's e negative the opposite the integral of this dx. We can substitute back into the previous equation. We get y equals, instead of y1, e negative integral p of x dx, the integral of f of x dx over e negative integral p of x dx. This here, this form, you can bring this up now by rewriting it. E negative p of x dx, the integral of p of x dx times f of x dx, which really proves, let's call this equation, this one called equation 3. So that proves equation 3, the particle solution. So what we actually did here, we re-derived equation 3 above using a method called variation of parameters, where the u1 is used. How about if it's a second? If we're working with second order, y double prime plus p of x y prime plus q of x y equals f of x. That's called equation 4. Now the question is how to find the particular solution. So the first thing we do, we can make it as a homogeneous, and find YC, the complementary solution, with two functions because it's a second degree order. Call them y1 and y2 as solutions. So in this case, y particular is going to be not just y1 u1 y1, but also plus as a linear combination y2 u2. What happens if we do it this way? Well, it's going to give us the derivative of this using product rule, u1 prime y1 plus u1 y prime y1 prime plus u2 prime y2 plus u2 y2 prime. Now we are going to arrange these terms. Keep the u1 y1 prime by itself plus u2 y2 prime by itself. So these two together, plus the rest can be rewritten next to each other like so. We are going to call this equation 5. And what I'm going to do, I'm going to assume this is 0 by assumption, and for simplicity to derive the solutions. So then that will give me just y p prime to be u1 y1 prime plus u2 y2 prime. From here, I need to find the second derivative by the product rule again. u1 y1 double prime plus y1 prime y1 prime. u2 prime y2 prime plus u2 y2 double prime. Now we substitute what we just found into equation 4 above. So we had y double prime p plus p y prime p plus q y p, and let's see what we get. We get u1, when you substitute everything and group them up, you get y1 double prime p y1 prime plus q y1 plus u2 y2 double prime plus p y2 prime plus q y2 plus u1 prime y1 prime plus u2 prime y2 prime equals f of x. These two here are zeros. This one is 0 and this is 0. By similar reasoning as we did in the first order differential equation. So that will leave us only with y1 prime u1 prime y1 prime plus u2 prime y2 prime equals f of x. Now what do we have here? From number 5 there, or this one, from 5, and let's call this 6. From 5 and 6, we can rewrite them as a system of equations. The first one, y1 u1 prime, y2 u2 prime, that's from 5. From 6, u1 prime y1 prime plus u2 prime y2 prime equals f of x. Here we have y1 and y2 are known to us. They will be known. The question is, what is y1 prime and what is y2 prime? Those, the variations of parameters, what are they? So to do that, we can solve this system of equations using Kramer's rule. You can review what that is to get. I'm not going to show the steps for the Kramer's rule, but you can review it and see it's not difficult to find u1 prime to be w1 over w, and u2 prime is w2 over w. And what is w? W is basically the coefficients from the system of equations y1, y2, y2 prime, y1 prime, y2 prime. So these are the coefficients, this, 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 and this. Because remember, the u's are the variables, and the other ones are known, means they're constants. Think about this way. And w1 is the one where you drop the y1s, like y1, y1 prime, and replace them with the right hand side, 0 f of x. And this stays the same, y2, y2 prime. For w2, keep the first one the same, y1, y1 prime, and you drop the y2s, replace them with 0 and f of x. These are determinants. So, in summary, I like to summarize it, what we just did in this section. If we are given a second order differential equation, we find yc by using c1 y1 plus c2 y2, where y1 y2 are the solutions. That's the complementary solution. Then we find, as a next step, w, which is the determinant, y1 y1 prime, y2 y2 prime. Then we find the w1 and w2. So w1, we told you 0 f of x, y2 y2 prime, and w2 is y1 y1 prime, 0 f of x. And after we find these, that will enable us to find y1 and y2. So we find y1 and y2 by integrating u1 prime, which we told you it's w1 over w, and u2 prime, which is w2 over w. Then from here we can find the particular solution, which we told you it's u1 y1 plus u2 y2. And as a final step, we can get the general solution from yc and yp. Let's look at an example from the textbook. Solve y double prime minus 4y prime plus 4y equals x plus 1 e to the 2x. First, we try to find the yc, the complementary solution. So how do you find the complementary solution? We get the characteristic equation m squared minus 4m plus 4 equals to 0. Factor this out, m minus 2, m minus 2, so square. So the m's is going to be 2 or 2. So yc would be c1 e to the 2x plus c2 x e to the 2x because of the repetition. That's yc. Now from here, this is the y1. This is the y2. So y1 is e to the 2x and y2 is x e to the 2x. We can find w. W is what? y1, y2, so y1, y2. And we're going to find the derivative for this, which is 2e to the 2x. Derivative of this by the product rule, 2x plus 2x e to the 2x. Multiply this out. Let's see what we get. Cross multiply e to the 4x plus 2x e to the 4x minus 2x e to the 4x. These cancel out, so you get e to the 4x. That's w. We need to find w1. 0 and the function on the right side, which was this. And here this stays the same. And we found its derivative 2x e to the 2x plus e to the 2x. If you multiply that out, this will go to 0, so that will give us negative x plus 1 times x times e to the 4x, as you add the exponents. And for w2, keep e to the 2x the same, replace this with 0 and the function x plus 1 e to the 2x, and the derivative of this is 2e to the 2x. Cross multiply, that'll give us x plus 1 e to the 4x. From here you can find u1 prime, which is w1 over w. w1, it's negative x plus 1 times x e to the 4x, and w is e to the 4x. That gives us negative x squared minus x. u2 prime is w2 over w, which is x plus 1 e to the 4x over e to the 4x. From u1 prime, we can find u1 by integrating both sides. So integrating this negative x squared minus x dx. That gives negative x cubed over 3 minus x squared over 2. No need for constants because we're already going to have a lot of constants there. y2, the same thing, x plus 1 dx, which is x squared over 2 plus x. No need for constants. That will give me yp. Yp is u1 y1 plus u2 y2. So yp is y1 is negative x cubed over 3 minus x squared over 2. y1 is e to the 2x plus x squared over 2 plus x times x e to the 2x. That's the particular solution, which we can simplify actually by factoring e to the 2x out. Negative x cubed over 3 minus x squared over 2 plus x squared over 2 plus x. Notice these cancel out. So y particular is actually no, there's a cube here. a square there. So these combine to x cubed over 6, and these two combine to plus x squared over 2, e to the 2x. That's the particular solution. Therefore, the general solution is yc plus yp. Yc, we found it was c1 e to the 2x plus c2x e to the 2x plus the one we just found, x cubed over 6 plus x squared over 2 e to the 2x. That's the general solution. All the examples will be followed the same way, can be resolved the same way. One other example from the book: solve 4y double prime plus 36y equals cosecant 3x. So why are we using variation of parameters method here? Because if you want to do the annihilator method from the last two sections, we cannot annihilate the cosecant 3x. So note on the side, we cannot cosecant 3x. So the variation of parameters method works here. It will help us to solve the differential equation. First thing I would do, I would divide everything by 4. So y double prime plus 9y equals 1/4 cosecant 3x. Then we get the characteristic equation m squared plus 9 equals 0. M squared is -9, so m is plus or minus 3i. So then yc is c1 cosine 3x plus c2 sine 3x. So this is again y1, this is y2, y1 and y2. From y1 we need that, and y2. So what we can do, we can get the w. W is y1 sine 3x, y2, then y1 prime is -3 sine 3x and 3 cosine 3x. Cross multiply, we get 3 cosine square 3x plus 3 sine square 3x. Take a 3 out, and cosine square plus sine square is 1. That's w. We need to find w1. 0, 1/4 cosecant 3x and sine 3x, 3 cosine 3x. 0 minus, it's -1/4. Cosecant times sine goes away, it's 1. w2 cosine 3x, -3 sine 3x. And here we have the 0, 1/4 cosecant 3x. When we multiply it out, you get 1/4 cosecant 3x times cosecant, which is 1 over sine, so sine 3x. Now u1 prime is w1 over w. w1 is -1/4, and w was 3. So it's -1 over 12. And u2 prime is w2 over w. w2 is 1/4 cosine 3x over sine 3x, and w is 3. So that gives us 1 over 12 cosine 3x over sine 3x. I'm leaving it like this. You can write as cotangent if you like, but later when I integrate, it's simpler this way. So from here, from u1 prime, you can integrate. You get u1 equals the integral of -1 over 12 dx Same thing from u2 prime. u2 is the integral of 1 over 12 cosine 3x over sine 3x dx. First one is easy to integrate, is negative 112x, but the other one you can use u sub as sine 3x. So du is 3 cosine 3x dx. So then you need a 3 here and 1/3 out. So u2 equals 1 over 36 natural log of the opposite value of sine 3x. No need for constants. Then the particular solution, it's u1 y1 plus u2 y2. Negative 1 over 12x. y1 was cosine 3x. u2 is 1 over 36 natural log of the opposite value of sine 3x. And u2 is sine 3x. This is the particular. Then the general solution is yc plus yp. So yc is c1 cosine 3x we found earlier plus c2 sine 3x, and the particular solution is the one we just found. We can just copy it down. Again, all the problems using variation parameters, they follow the same steps by finding the yc first and find w, w1, w2. From there you find u1 prime, u2 prime. Integrate to find u1 and u2. From u1 and u2 with the y1, y2 you can find the particular, and then add them. Add the particular with yc, the complementary solutions, to get the general solutions.